In this first week, we'll begin to look at the context within which these large software systems are developed. In particular, we're going to look at how we got to the software engineering techniques that we use today. We need to understand the history to be able to understand where we need to go from here. Obviously, the first decade of the 21st century has left us with bigger, more complex systems. We're depending more on software. We have to develop things more quickly. And we really haven't had a lot of luck building the systems we've tried to build today. There are a lot of reasons how we've gotten here, but it's really not a new situation for software engineers. In the remainder of this lecture, we'll use a lot of the ideas that Barry Boehm put forth in his 2006 keynote address at ICSE. We'll first look at some motivation of why we even care about history. We'll talk about the 20th and 21st centuries, and then we'll have some principles, both good and bad, to look at the end. Of course, George Santayana's famous quote comes to mind, but it really is only a half-truth. We certainly don't want to repeat the failures, but we sure would like to repeat the successes. Unfortunately, we are really losing our history. So many great software engineering heroes are gone. Grace Hopper, Harlan Mills, Winston Royce, Edsger Dijkstra, Dahl and Nygaard. And to make matters worse, most of the students today, and researchers in general, make their references over the web or with digital libraries, and they don't go back to the point where there were actually real, honest-to-God papers. Georg Wilhelm Friedrich Hegel developed a specific philosophical system to help look at opposing ideas. The concepts of thesis, antithesis, and synthesis operate to ultimately integrate and unite two concepts without eliminating either pole or reducing it to just one or the other. This diagram shows the interplay between thesis, synthesis, and antithesis. We'll need to look more closely to make some sense of this. So all aboard for our Hegelian romp through the 20th century. The 50s, post-war America, the beginning of the Cold War, the work of Alan Turing and John von Neumann led to the rise of IBM and other companies, and yes, even to Fortran. Software was treated just like hardware, and most of the applications dealt with hardware design. The economics was such that obviously the computer was much more expensive than the people programming it, so there was a lot of pre-work and verification and desk work that we don't see much anymore. There were some professional societies begun, but they all sounded like hardware. Software processes were pretty much straight out of engineering. An example would be SAGE, the semi-automated ground environment. Unlike Wilson Pickett in the 60s, we learned that software wasn't as easy as 1, 2, 3. Fred Brooks, 20 years later, described the problem succinctly in his classic paper, No Silver Bullet. The four werewolves were invisibility, software just can't be seen, complexity, there can be billions and billions of states that are non-continuous, conformity, even a semicolon out of place can cause a disaster, and changeability, it's so easy to change software. And a decade later, Brooks said, everything is still true, all four werewolves are alive and well. The 60s saw software going from being made like hardware to being crafted like art. The demand for software engineers exceeded the supply of traditionally trained engineers, and what we got was a lot of people who couldn't get jobs in other places. Support technology was getting better because Moore's Law was beginning to kick in and more computer power was available. We were beginning to get families of products, and we actually had some large successes. Unfortunately, it was also the birth of many of our problems today. Enter the 70s. To address those problems, the 70s turned to process, formal methods, the waterfall approach, a way of looking at doing software where the process controlled the quality. The waterfall processes came into being because it cost much more to fix a problem later in the life cycle, and so the obvious answer was to make sure that everything happens right the first time. Because of this, requirements became much more important, and every phase became established only when the phase before it was completed. Of course, there were problems with formal methods as well. They only seemed to work on small programs, and even then they only showed the presence of defects. They didn't prove the absence. They weren't scalable, and they required a lot of mathematics. We begin to see another change in economics, in a flip-flop of the hardware and software costs. Of course, there are problems with the waterfall method. Unfortunately, it was really interpreted one time through. You ended up with heavyweight documentation. Unfortunately, it doesn't match when you're trying to use COTS or legacy software. And of course, Moore's Law wrought havoc on all of these long waterfall-based schedules. In the 1980s, we now had a synthesis from these two sets of problems, and that was productivity. We began to look at reuse, and we began to look at object-oriented techniques. Everyone was looking for more producibility, more productivity. We began to get tool support, process-driven software engineering environments. Software processes were executable because software processes were software too. And there became a major emphasis on process compliance, with capability maturity models leading the charge. One of the forgotten issues in this rush to process was that software has always been extremely people-intensive, and much work has been done on that subject. And as Toulin says in Cosmopolis, there's a move from reductionism, looking at things in smaller and smaller pieces, to one of more postmodernism and a more holistic worldview. At the end of the 1990s and the early 2000s, we began to have this antithesis come out again that said we really wanted to have these methods that were predictable and under control, and maturity models seemed to bring that. And yet the real world was changing so rapidly. We had emergent properties, we had fast time to markets, we needed something very agile. Of course, about this time the Y2K issues came up and we started to have to reverse engineer everything. There was the idea of risk-driven concurrent engineering that came out of the spiral models. We began to see more COTS, more open source and legacy software, and software was essentially becoming the prime competitive discriminator between companies. The result was a synthesis that led to risk-driven hybrid products, integrating systems engineering and software engineering, focusing on value and the user, model-driven development, new architectures, the understanding that requirements are emergent, not necessarily pre-specifiable, and the merger of agile and plan-driven approaches brought about new ways to look at process architectures. Is the future of systems and software? Well, we're going to look at a number of trends, 8 of which we think are pretty much surprise-free, and a couple of other wildcards. Obviously, systems and software are going to have to be integrated more. We're going to see more focus on users and value. Software is going to become much more critical and will need to be more dependable. We'll continue to see change. We'll see broader distributed systems with all of those kinds of issues. Systems will continue to get more complex, including ultra-large systems. We'll see more brownfield systems than greenfield systems. And of course, Moore's Law will continue, and we'll have computers everywhere. And those two wildcard trends are autonomic software, that is, software that thinks for itself and performs based on its own decision-making capabilities. And the second is a mixture of biology and computing, whether that's nanocytes injected into your bloodstream or whether it's a chip implanted in your brain. Let's look more closely at a few of these trends. Globalization. Tom Friedman's The World is Flat postulates a world with the communications and computing technology so diverse and so widespread that becomes a much more egalitarian business environment where almost everybody can get a leg up. But there are risks, and you need new competitive strategies to keep ahead. Have you ever wondered why the cities of today don't look like those modern cities as they were projected in science fiction? Well, one reason is because everything generally is based on legacy systems, and that legacy constrains systems evolution from now on. Computational plenty is both a blessing and a curse. On the one hand, you're going to have enough power to do just about anything you want to do. On the other hand, think about all of the work that's going to have to be done to make all of these things that we're doing actually of high quality and meeting all of the various safety and security and assurance requirements. Like computational plenty, the autonomy and biocomputing have a lot of potential for good, but the potential for harm represents significant risk. Now let's look at some of those principles we talked about. Of course, the timeless principles are things we want to do, and the aging practices are things that are probably not good to hang on to. From the 1950s, we want to hold on to our technological and engineering backgrounds, be careful about what we want to do, and to try not to let process drive everything. From the 1960s, we remember that software is truly different, but that those differences allow us to have a broader perspective in approaching problems. In the 70s, we see error elimination's good, but you really want to avoid top-down development and the reductionism that results. Of course, there are many roads to increase productivity, but always be skeptical about silver bullets. From the 90s, we've learned that it's important to maintain the values of people, make software useful to the people. And also, we've learned that it's not a good idea to hurry too quickly through software development. In the 2000s, we learned that rapid change means that adaptability is much more important than repeatability or maturity. It's also important to remember that there are lots of stakeholders and you'll need to satisfice between them in order to have a successful project. Most importantly, try to avoid falling in love with your slogans. And what we can look for in the future is watching out that we don't continue to try to build things that we don't know how to build, know when to hold them and know when to fold them, and of course, don't believe everything you read on the internet. This completes our first week's lecture. All of the homework and readings and other videos are available on the web. Thanks for watching this, and I'll look forward to seeing you next week.